and we'll get started. So the first tutorial will be about multi-messenger astronomy with ObsTAP and pyVO. And we'll see soon, very, very soon. Hendrik, I'm sure, is setting up his laptop and getting all the software ready and, you know, his internet connection and all this kind of stuff. Okay, Hendrik is here. I see him here. Excellent. So Hendrik, you can start whenever you want.
So good morning. I'm Hendrik, and I will present together with Dave Morris. Is Dave here already?
I am indeed.
Late. Oh, you are. Hello. Yeah, we will present a use case in this morning about pyVO and multi-messenger astronomy with ObsTAP and pyVO. And we are a bit happy to open the ADES 2020 to be the opening gig here. And yeah, and a bit excited, of course, to do the first virtual meeting here and the first virtual tutorial, which means all of you basically are guinea pigs, and we figure out how that might work. To line out, I will point you to a GitHub repository where we put everything, where we have all the files and the outline of this tutorial collected so that you find it all at one spot. You do not necessarily need to check out the repository at this time, but there is at least the PDF file in the main folder that you could use. I will provide a link in the chat when I see the chat again here. So we only have questions and answers, right? No open questions.
That's it, yeah. Yeah.
You can always use Discord for this type of links so that they will also stay around, because Zoom, everything will appear and disappear depending on when people come and go. Okay, which is the best channel to post this? Just put it under talks so that also people can see it later on. Some people will watch these tutorials at some other time, maybe this afternoon, maybe tomorrow. So it would be nice if they could have some important links, and I can always pin them so that they will always be around. Yeah. So I just sent the link to the on Discord. So that you can all access this, hopefully. So yeah, what are we going to do today is we are going to present a use case of multi-messenger astronomy and VO, and especially with pyVO. We admit we are no astronomers, so don't expect this to be as fancy as it may sound, and don't expect Dave and me to have a major scientific breakthrough on the hand here. That we don't, but what we do have is we put together a few standards from the VO, together with neutrino data, together with SDSS data, and with the standards, especially the standard of ObsTAP and ObsCore. And we will show you how to use pyVO to explore these data and to access the data especially. The tutorial will have two bigger parts. In the first part, we will introduce a bit into the standards, and therefore we will use Topcat and not pyVO.
just to show what are the standards that we're talking about. And this might be necessary because people might not be familiar with the standards, and then it's a bit an overkill to show how to access a standard from within a script or from Python code, and when you are not familiar yet. So we will introduce a few standards from Topcat, and then in the second part of the tutorial, then we will use pyVO to show you, well, how to use these standards that we introduced from pyVO, and then especially how to use the ObsCore services out there, how to find ObsCore services and to use the ObsCore services, so that you can actually perform all VO queries from within pyVO. So yeah, somebody has a cat. Good morning. We start out with, I have a terminal here, which I will make a bit bigger so that you might see what am I actually doing here. I downloaded these scripts into the folder. I have a GitHub folder as with the repository that we used, and there I also have provide links to Aladin and Topcat so that you may use them later on. These are not the, we don't provide you with the software itself, but in the folder bin, you will find a install script. This script install that you simply can use from your bash will download Aladin and Topcat so you can use them, and as well as you find these two, and you find, oh, sorry, I need to share my screen, right? I'm very sorry for this. So again, so I just told you. So the Git repository that we're using is Hyantis. If you download this repository, then you see basically the folder Aladin bin, PySources and README. README describes you a bit what to do, and you have Topcat. If you just go into the folder and bin, then you find an install script which will download the latest version of Aladin and the latest version of Topcat, and you can use the scripts in here to start the software itself. So yeah, I will start out with Topcat. And wait a second until Topcat is started here. Here we go. So I have Topcat on my machine here. This is the Topcat main window, and Topcat is a software developed by Mark Taylor, who is with us this morning. Topcat is developed especially for the use with table data. And it provides several interfaces to the VO. And feasible for us is that they are summed up basically under the tab VO here. And we will start with the VO cone search protocol. So simply clicking on the cone search will open the cone search window. And the cone search is one of the early protocols on the VO. And I will just show you what are the steps that we are using in Topcat very fastly, and then we will slow down and repeat the steps, and then you get the idea, and we will talk about the actual protocols in the background. So what I'm going to do is I'm going to search for neutrino data here, and search for the services that are out there. And I find a list of neutrino data here. For one reason or the other, I will select the cone search service for the Antares neutrino data provided by KM3net. And if you're searching for data, you can see this in this field here. You can see the metadata on the services, and you might you might come to a different solution, what suits you best. We will go to perform a cone search on this data and just simply say, well, take this position and a radius of 30 degrees around this position, and now get me the data from there. And you see that was a pretty fast search here, and I have the result in the Topcat main window now, and I have 280 rows. So these are the data points. I can already do things with these data points. For instance, I can do a fast sky plot simply by clicking on this small button here. Then you see this is roughly, maybe I'll do it this way. This is roughly a big, well, you see the shape. There is almost a circle, or you can think of the idea of the circle, which is, well, not big a clue because we downloaded, we made a cone selection, so we basically gave a radius, so we have it here. And again, what we did yet so far, we used just a bit of the VO to access this data, download the data, but we also used a bit of the VO to plot the data, because so far I did not do much to select any data or to tell the plot what to do. But Topcat has a pretty good idea that where to find the position within the data, and this can be due to metadata that we provide, in this case, so-called UCDs. I can use Topcat to have a look on the metadata that I just said. So this is the metadata on the columns that I have in my table. So of interest for me might be, well, the time, might be, of course, the position. It might be the angular error, the estimation for reconstruction. Keep that in mind. Have a look on that. We will use that later on. But of course, we promised we're going to combine data. This is neutrino data. Now, let's go for a different for a different observation. Maybe now let's have a look at catalog data and see if we can obtain some colors from catalog data that is out there. And for this, we want to check a remote service providing us with data. We are not using the cone search for this. For this, we are going to use the TAP service, which again is a VO service and a VO standard. TAP stands for Table Access Protocol. And you see we open that. We have a list of TAP services here. And now I'm going to search for SDSS colors here. So I type in the keywords simply SDSS, search for the services, and again get a bunch of services. I mean, SDSS, of course, I see a lot in Vizier. SDSS is a widely used service, a survey. So we many data centers offer data here. For the sake of the tutorial, we use the GAVO data service. Later on, we might explain what we are actually doing and why we're doing this. At this moment, you can just think about, well, I make an elaborate guess. Indeed, what you actually can do is you can use these small buttons on the left here to see the actual tables on the TAP services or the catalogs that are related to the keyword that I searched for. So you see on GAVO there are a few services providing or are related to SDSS. If I do this on Vizier, well, you see there are hundreds of tables, of course, because many of SDSS colors or SDSS data is used in papers and published on Vizier then. And here we see the GAVO data center, and we can have a guess that this table here, SDSS DR7 sources, might be the one of interest. It's a bit outdated, of course. I think it's the most recent version is SDSS DR13, but we used DR7 here just for performance reasons. I clicked on use service, and it took a few seconds until this this tree popped up here. And well, this is the table access protocol tree that provides me with the possibility to get some information about the service itself and about the table and the catalogs that are provided on the service. Again, in a bit, we will be talking about what that actually means and what we can do with all of that. I used the fancy search up here so that I don't have to scroll through all the tables down, and I see the SDSS table here. I can simply, what I want to do, of course, now is to check for all my 280 sources that I have here. I want to check if there is any data in the SDSS nearby, if I can take any colors for that. Now, if I look into the column metadata, then I see, oh, there is a lot of columns that I actually don't want to. And so I want to not to get everything, but from what is offered here. And of course, somehow I need to combine my data. Now, TAP and ADQL are very nice because they provide us with the possibility of bringing code to the data to the code. No, code to the data, sorry, and part of my data as well. And this I can do using the example of an upload joint here. Again, you see that Topcat had a good guess of where might be positions in SDSS and where might be positions in my local data, which I have here. But what I don't want to have is in the query, this line here. We will later explain what this query means. For now, you just have to know this query will help me a lot to obtain colors and some data from SDSS. Now, I will just mark a few columns on the left, on the right, from the right window here, which are the columns that I'm interested in. And again, we'll use Topcat to, because I'm lazy, I just want to make the selection in Topcat easy for me. I need to do something like this at one point. Again, later we will explain what that means. Maybe 5 arc seconds is a bit slow here. We also explain what that will mean and below. So far, not of importance. I will just run the query. And yep, took just a few seconds. You see, it's a fast step. And I combined my neutrino data from the cone search that I had here with, well, some data here. I can prove that actually in having a look into the metadata here. So extending this. Then, oh, you see, I made a mistake because I did not combine. Maybe I think some may have noticed that before. So what I need to do, of course, is this to combine. Sorry for this. But everything is fast. Now I did combine this data, as you see now. Yeah, here is the data that you knew, and the including the event identifier. This is the neutrino data that we got from the cone search service from KM3net, and the data below that, and these columns here, is the data that we just combined from the SDSS service, from the SDSS table on the GAWO data service. Of course, I can look into the data itself and start combining or making signs on this data, which I can't because I'm from the programming side. Again, I can use the sky plot to have a look at the sky, and I could maybe, if I'm interested, I could use plane plots in Topcat now to make color cuts of the data that I have. I don't know, I could use the I band in the one and the I band minus the R band in the other, just to see. Yeah, doesn't say anything to me now, but it's 54 data points. So this is just a short explanation on how I easily can combine data. using the cone search service to obtain the neutrino data from KM3net, which is the Antares data from 2007 until 2017, so 10 years of observation there, and use a table access protocol to combine that with data from other sources online. Now, that was very fast, and what actually happens in the background is, of course, of interest, and we are going to repeat these exact steps now and elaborate a bit on the data services or on the standards, VO standards, that we do have. And indeed, I will start this. I will close and will shut down Topcat and start from scratch with it, so that we have a vanilla version here. So this is my Topcat window that I use to start out the whole process. And again, I know what I'm going to search for. I'm going to search for neutrino data, and I want to start with a cone search for that. And I open the cone search window. And here I see I can have something like keywords here where I can simply type in neutrino and click on find service, and some magic happens. And I think Dave is explaining this magic now a bit.
Yeah, so what's happened underneath behind this is Topcat has sent a query to the IVOA registry, which contains metadata about all of the available services within the VO. So this is one of the successes of the registry group, is reaching a common understanding of how to describe services, both their technical capabilities, but also the semantics of metadata, so that the how to describe, for instance, the keywords like neutrino and what that means. So all the services that are registered use the same semantics, so that queries like this find consistent services. What this has done is queried the registry and got back a list of the services, that the type of services that Hendrik requested, which is cone search services. Yeah. So if he moves down to the panel below, so sorry, first of all, he selects the services interested in, and here he's selecting by, it's displaying the name of, it's got Antares data. So this is the one he's interested in. And so he's now going to fill in the parameters for the service. So the other part of this is that all the services have a standard interface. So all the cone search services have a standard set of parameters. So the IVOA standard for the cone search, which is one of the first standards that was ever defined, I think, in the IVOA way back in, I think, 2006 was the original definition of this. The parameters that he's putting in there are common to all cone search services. So Topcat can send the same query to all of the services and get a standard set of results back. Okay, so do you want to go for it? And
yep. So you see, we just obtained our neutrino data. I will just briefly go back to the cone search to give an example of what Dave just said. So if I, instead of neutrino, if I type, I don't know, if I just try gamma ray at this point, I don't know if I find something, I will just search for that. Then the registry is searched, and now I find services, cone search services, providing me with gamma ray data. And you see, well, apparently there is more to say so far about gamma ray than about neutrinos, because if you compare that neutrino to the amount of services that are found for neutrino, well, there basically is it's not much in there so far. That hopefully changes in a not too far future. So we have our local data from the neutrino cone search service, and as said before, I can have a look into the metadata here, and I can see well, I can see the columns that I have. So I have 280 columns here. I have a look into the actual data. I have the metadata here, and the metadata provides me with one special thing, which is, of course, the description, and I can have units here, but one special thing that I find in the metadata are the so-called UCDs, Unified Content Descriptors. We will find these in several points again, and at a later stage we will talk about what these are meant for. But it's good that you know they are there. They are a bit of the secret of the semantics, and they are helping us a lot in the VO at several points. We make use of them very, very often. So I had the local data here and my 280 rows. And the goal was that we obtain colors from SDSS, and we wanted to do this by using the table access protocol, because that's catalog data, and there is a lot of catalogs out there. And well, we're going to do this way. Of course, if you think about this, I could as well just have taken the cone search protocol and said, well, what's wrong with searching for SDSS and then using the cone search protocol to query an SDSS service if there is one out there. I don't even know if there is. Yeah, there is. That's so I could use the cone search here, but as you see, I'm not mad. This is a 30 degrees radius around this position. If I now download all the data in there, but that might take a while, and it's a bit unfriendly to do so, I think, because cone search is a very cost-intensive protocol for the services. So I won't do that because I can expect, if I do this query, that I get millions of rows back as a result of this query. But I already know that I only have 280 neutrino events here. So I strongly doubt that I'm interested in million data points from SDSS. So I'm trying a smarter version, and the smarter version will be the table access protocol, which gives me a bit more power about on the selection that I actually want to make, reducing the actual size of data that I have to handle. So again, I have a field with keywords in here that I can use. And here I type SDSS. And I see the list of services here again. These are the TAP services providing me with SDSS, with data that has SDSS in the table description. That does not necessarily mean that I get the full SDSS data from these services. It can simply mean that there is a table on the service that collected colors from 2MAS and SDSS, so that a subset of the data that is contained in SDSS is published there. But again, I can use this very same window here to explore the services and to figure out what's the kind of data that is provided by the service. And of course, also what is the name of the table that is providing this data, which gives me a good hint about which service I actually want to query. Mm-hmm. Now, we just assume I did this, and I decided I'm going for the GAVO data center here. And yep, I decide, well, let's get the GAVO data center and have a look at the service.
Okay, so what's happening here is Topcat is now sending a query, having once Hendrik has chosen that the service he's interested in, it's now sending a query to the service itself to find out what tables, the schema of the database that it's providing. So what the tables are, what the columns are, what their units are, etc. And this is another part of the standard for the TAP service. All TAP services provide this mechanism for discovering the table structure inside the service. So Topcat can apply this view to any of the TAP services that Hendrik chooses.
Yeah, so you see on the left, I have the tree of the catalogs and containing tables, and I can use the find on the top to reduce the data to SDSS. Give you that in the Garvo data center. It's not hard to scroll down. Try the same in Vizier to figure out where you are. Then this small little window here up here is very, 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 very feasible. Now, I can use, as Dave just said, I can use the TAP window here for data exploration. I can have information on the service. This is the information on the whole service. I can read about the schema, the TAP schema of the service. I can read about information about this very table, what's contained in here, where did it come from, what can I do with it. And very important for the queries to discover is what's actually in the columns. And we talked about this before regarding the columns, and we're talking about the metadata on the column. So you see I have the name of the column, and of course I can easily get that OBG stands for object, and RA and DEC, well, are very self-explaining. But I already need to know a bit more to understand that U marks a magnitude in U-band. And the same goes for G maybe, or R, if I'm not familiar with magnitudes and colors. So how do I actually deal with this data, and how do I figure out what data I'm interested in? I can use something. On the one hand, I can read the explanation and the description here, but I can use something which actually is not meant for humans to read, because it's a bit ugly in the first glance, and that's these unified content descriptors we were referring to earlier, which are the semantics. And if I read them right, which I now try to do, and I can sort them, then I'm interested in colors, then I simply know, I simply know that when I was searching for colors, well, they start with photometry, photmag, emission lines. And if I know a little more, then I know, for instance, that that if I have positions like these, and I have followed by meta main, that I immediately know, well, this is the position of the in this database. And at this very moment, you get an idea what's happening in Topcat if I click on the sky plot just on the ear, because this is not guessed, not a good guess only. It's simply the UCDs in the table, in the metadata of the table, that provides me with the information where can I find the positions. And the same goes for the TAP services. So you see that within the VO, we try to carry this kind of information, the metadata on the data, we try to carry this kind of information across the protocols that we use. So you will have the UCDs, for instance, on the server side. When you download them, you have them on your client side in your local data. When you save the data to your hard drive, you will have the, well, you have the possibility, you don't have to do it, but you, of course, you can simply save a CSV file if you really want to. But actually, it would be a bit smarter to save VO tables, because in VO tables you keep this kind of information, and you can use it later much more easy for that. So
can I just add a supplement to that? One of the things that we discovered very early on in the IVOA was that for a lot of database systems, the word DEC, DEC, actually was a reserved word in their language. So a lot of catalog archives used some variant of DEC for declination, so DECL, or they prefixed it with something. So the names across the various catalog services, the name of the declination field was not consistent. But because we use the UCDs, so the machine reads the UCDs, and that is always consistent.
So now about the step to combine the data. If I click on examples down here, I did so because I'm lazy. I didn't want to write everything. So I used to say I clicked on the upload join, which now in this lower window you see this is the ADQL part here. ADQL is the astronomical data query language, and it's built on SQL, and TAP and ADQL always compared. So where there is a TAP service, you can use ADQL, and to use ADQL, well, you need a TAP service. ADQL is more than SQL in many regards. First of all, you can use it to define regions and to make queries according to regions on a sphere. So for spherical data, which is the typical thing of RA and DEC, so the positions that we want to have, you can define, you can compare regions according to their location on the sky. And this is exactly what we're doing here in this query right here. So what happens? We have a select statement. Well, that's how ADQL starts, how every or SQL starts, because, well, we select something from something. What do we select? We select top 1,000. That just means we take the first results, the first 1,000 results. It's not in an order. That's quite important. So if I if I have this here, and I may have more than 1,000 results, so it could easily be that I write a query where I can expect 10,000 data records as a result, but I just want to explore it, so I take the first 1,000. 1,000 here means simply the first 1,000 results coming in. The order is, well, how the database just decided to process the data in the database. So there is no order in there. Actually, it's well, maybe not totally random, but pretty much arbitrary. So so it might, though top might imply that it's not, and there is no order. Pure vanilla SQL would have had the word limit here, which is a bit better explaining actually, but in ADQL, well, we have to live with this top now. So top 1,000, so we say, well, I don't expect more than 1,000 results from the query, which is quite reasonable given that I only have 280 neutrino events. Then I have this asterisk here, which is again kind of the wildcard, but it does just simply means select everything. Now, I don't want to select everything as before. What I want to select is I want to keep all of these columns. I can refer to all of these comments in by the way, in the way that I simply say I use TC dot this star. This TC I can use because it's defined at this position here. What tab upload means, we will see in a minute. But here I say as TC, and this is just an alias. This is not a variable. SQL does not have variables. SQL has aliases, and those are behave pretty different than variables. So don't confuse those. Yeah, I can use this now to refer to, well, all the columns that are contained in this table. And then I have the other table, which is the database. And you see Topcat, per default, Topcat use the name database for the data remote database, and TC, the abbreviation for Topcat for the local data. Now, what I wanted to select were a few columns here. So I will do this again. So I already marked RA and DEC here. That was what I wanted to have here. But I also wanted the object type, the object ID, sorry. And again, I wanted to mark the photometry. Oh, now I have something wrong here. I wanted to see the photometry here. So, which I assume if I mark simply all of these, that I have the bands over here. That's true. This is the wrong selection. This is the right selection. So I take all the magnitudes and the different color bands. And now I do a bit of a trick because I'm lazy and I don't want to type that. I will simply use this to get all of these down here. But I lost apparently RA and DEC. Yep. So I will also mark these again and say I want these. Then you see there is something going wrong. And here you see Topcat tells me something's wrong with this one here. And what's wrong with this RA definitely is it's not unique. So if I'm referring to this column is not unique amongst the both tables that I'm comparing. So I have RA here, and though this is in capitals, SQL is not case sensitive. So I have RA in this, and I have RA in here. So I need to add something to make sure, or to tell the database, well, what column am I referring here to actually? And I'm referring to the database side of the column, so I can do that. I have to give that. I don't need to give that, for instance, here. I can do that. That's not a mistake. It's not simply not necessary to do so, but I can do this because DEC is unique. As you see, it's DECL here with an L in the end. So this is what I want to select here. What more will I want to do? Well, I select from the SDS SDR7 table here, and I join the tab upload of T1. T1 here is referring to the table 1 here. And the tab upload is simply, I take my local data here, these 280 rows. And instead of downloading the whole SDSS, performing the cross-match and kicking out all the things that I don't need, I'm uploading my 280 rows here, which is very small, and let the remote database do the hard work and just enjoy that I get back the result. So this indeed is a version of bringing the code, and in this code here, to the data, which is this data here, and I give you that as the table here, and I have to upload a small amount of my own data to combine the two. Of course, if a service provides you with both of the data, so if we had a service providing me with the Antares data and at the same time with the SDSS data, that would be very feasible, because then I could use this very service to perform that and wouldn't need to perform a tab upload. And that indeed is the reason why many data providers keep or also publish these surveys, the big surveys, because then users can easily perform cross matches remotely on the services. So for instance, you will find 2MES and the SDSS data on the Gaia data services out there as well. Yeah, only change that I did here was I went for 10 instead of 5. This here, the definition of the radius is in degrees, in decimal degrees. So by this computation here, by this algebraic expression here, I can simply compute now 10 arc seconds, which is the range. I give the range so that we meet some of the data. But what I also could do is, if I use this beta here as an angular error estimate on reconstruction, then I could simply say, hey, hang on, I'm not using arc seconds here, I'm using beta here for that. I will not perform that due to the simple reason, if I have a look into the data, then I see, oh, this is immediately up to 1 degree that I have there, and with 280 objects, I will have too many results, so there will be too much uncertainty, and I will have too many objects to download maybe. So that, of course, is not very scientific. That decision just is due to the performance reasons. There is I don't want you to think that I'm assuming a precision by that. That's not given at all here, because if I wanted to do it actually in the right way, of course I would have to take into account the error on the position of the neutrino events. So this is what I run, and the result came back very, very easily. And I have the 54 results here, which now contain, well, yeah, my data that I had before, with including the event identifier, and now I added the magnitudes from SDSS, the object ID, which is the SDSS identifier, and also the position of the two, and they are now contained in this data, in my data here. This is what the data looks like with 54 rows. So what happens also is only positive matches are returned from this query. If I don't have matches, well, these are kicked out. If I have more than one match, well, then this is a positive match. All matches are returned. So it simply means that I have to take into I have to have a look into the data if that actually if I actually have more than one SDSS source that is corresponding with that. And if you look at here, then we have the case here that this is the Antares ID. Then you see that for this Antares ID, I already have at least 3 SDSS sources that are corresponding here. Of course, these are things you have to take into account, and you have to sort out eventually to see what's the most probable match that I can have here, based, well, on the science that you do, right? I give you that. I'm making it very easy here because I'm just combining neutrinos with colors. I'm not doing this on a science base. So this is so far the first bit of the tutorial that we have here. You see that we did not exactly follow the PDF file that we provided, which is okay. You can use the PDF file and what we have there standalone and follow that and use that to dig deeper. We will it's self-explanatory, and it will cover basically the same skills and knowledge that you have here, and the same standards. So I'd say before we continue with the pyVO part, I have a look at, do we have questions and answers, or how is this organized? Do we take questions now? Do we take them later? How do we plan that? Or how do you plan that, Francesco, maybe?
It's really up to you folks. Right now, there are no open questions. There were a few questions that were about, you know, the settings and stuff like that, more general than this tutorial, that were answered by us. But it's really up to you. If you want, I can interrupt you at the appropriate moment, of course, when a question arises that is, you know, on the topic. Or you can monitor the Q&A button it's really up to you. If you want to concentrate on the tutorial.
No, I'm fine. So I am very fine to be interrupted.
Okay.
I keep pestering people with the information that I'm not an astronomer, and there is a very important part in that. Please interrupt me if I'm being stupid, if I'm talking rubbish. Interrupt me, correct me. The worst thing that can happen is that I learn something new, and this is hilarious. Learning new stuff really is great. So please feel free to raise your hand, and Francesco, feel free to interrupt me if there is a question. That would be great. Yes.
Okay, so there are actually some questions that just popped up right now. Luis, for instance, is asking how the ADQL handles different databases at different services.
At different services. Yeah, not at all. Yeah, that's the sad truth. So far, ADQL, you can perform ADQL on different databases. Maybe we will show examples later where it's standardized. But performing an ADQL query, so if I say here, the selection of the service that I query is before I perform the query itself. Sorry, I have the participants maybe. So this query here that we have here is now optimized and customized from my side to my needs and to the server side. And ADQL itself does not correspond that I could now say somewhere in here use a join to refer to a different service. This I can't do. What I can do is using or joining tables on the same service and do something about that. But maybe I think Dave wants to say something.
Well, it depends on whether the question is, does it work between services? And I think you've answered that one, is no, that it doesn't. But ADQL hides the details of the individual services. So I'm not sure the context of the question. Was it querying two different services, or was it querying different types of services? Okay, there's one here. Do understand Topcat itself parses the ADQL? So Topcat parses the ADQL locally, yes, but then it's also sending the ADQL to the server as well. So there's some degree of parsing of the ADQL locally, so that it, as you say, it knows which table to upload. So both is the answer to that question. Can you upload multiple tables? I think the answer to that is yes.
Well, let's try.
Yeah. We actually have Mark Taylor on, actually, in the panel list. So Mark, can you actually upload multiple tables?
I don't, and I'm not sure if he can ask, if he can.
All right.
I don't know if you can hear me or not, but yes, you can upload multiple tables. And yes, Topcat does parse enough of the ADQL to work out which Topcat table that it needs to send to the server and sends that table. But then most of the ADQL understanding is done at the server end, but Topcat does understand it a bit.
Yeah. Cool, thanks.
So there is one person, Gabriel, who would like to ask another question. He had his hands up early on, so I will allow him to actually ask the question directly. So there you go. Gabriel, you can unmute yourself. And,
yeah. Hello, good morning. So I have the question, are there plans to make the TAP ADQL queries more robust? Because I think it works, but it's very capricious. if and I cannot play so much with the language like in Python. If I make like a Python script, and it's Python is it's reliable, and with ADQL it's really complicated, and if I find some kind of new quantity from other quantities, I have to copy paste it again and again, or it's complicated.
So the answer to that is no. No, and there's the reason is quite simple actually. ADQL is not a programming language, so you will never have the full power on what you want to perform as you are used to with Python. But the reason for that is simply these are two completely different use cases that you have. So Python is a Turing complete language. ADQL isn't. And so you don't have an if statement, for instance, in ADQL. And you want it to be that way because with ADQL, or with SQL, actually, which is the base of that, with SQL, you organize databases and you query databases. And to have a chance to gain some sort of reasoning about what's actually happening when I do that, which is important for the query planner underneath that is planning which query should be performed in which way. To have a reasoning on that, it's important that the query language that you use is not Turing complete, because if it was Turing complete, well, I could easily write queries that, well, nobody could tell when they will terminate. Well, I can write Turing machines, right? So that's the first thing here. The second thing here is that the database itself has to be prepared in a way that makes computation on the database or outside the logic of a database and the relations of a database easily a bit complicated. So you can see that if I go back to Topcat, it's now have to organize myself a bit here. If you look into the metadata window in Topcat here, then you see there is a column indexed, for instance. So there are now they're here. There are two columns that are indexed. Indexed means that the database prepares these two columns to be accessible very fastly because there will be a lot of access on these columns. Now, which basically means, well, it makes a lot of sense to put to index the positions, because that's the main data that will be accessed to perform cross matches between data sets. But whenever I start computing something, then the database is not prepared with the result. And by computing, I mean, if I define such a geometry down here, if I compute, for instance, I could take proper motions in the Gaia catalog and compute it from the proper motion in array and deck. I could compute the total proper motion. Then this proper motion is a new value, and with this, the database doesn't know anything of this new value, whereas the database knows a lot about these two values. Especially these values are in order in the database, so the database can easily access them. So there are limits. There are limits to ADQL. There are limits to SQL, and there will always be limits to SQL. What you gain with these limits is speed and performance when it comes to those data that is very well prepared in the database. There you gain, and the speed is the performance boost. Here we're talking about a performance boost by thousands in the speed of meaning of what you have to wait. So you can think about, if you download SDSS and process SDSS locally on a hard drive, takes hours. If I process SDSS in exactly this same way in a well-prepared database, it's seconds. So that's the reason why, or the reasons why you don't do that.
So it will be like appropriate to do it stepwise, to query what is really relevant, so not too much, and then the rest do it in the computer, like the rest of the processor.
You can do computations on the remote service. For instance, if you look here, you see here's an option asynchronous and synchronous. The standard option is synchronous, which means you expect a fast service, but there is also the asynchronous query, which means you expect that your query might take a bit longer. And which happens if you start computing something and then compare data sets based on the new results of your computation. Then you might want to use an asynchronous mode. A good hint in when you deal with databases always is take care if you really want to put things in order. If you really need the database to order things before you download them, that's easy if we're talking about data that's already indexed. That's not big an issue actually, but if you're talking about data that is computed or calculated by the database, and then you put it in order, like asking for, well, compute the total to proper motion overall Gaia objects, and then download the 10 fastest. Have fun. That's then that's really a thing, because then the database will have to compute everything to get you the 10 fastest, and that easily explodes the performance, or in the means of performance.
Yep. And last question, very quick, smaller. Is it possible to, like, if something is if one defines, for example, a new quantity, is it possible to store it and then to not having to copy paste it again, the whole operation in the
yes and no. What do you mean by store it? Do you mean is there a way to have it available now, or do you mean to store it like I want to store it here for the next 30 days and then reuse it?
No, I mean more like in a query when on this, for example, when it has to use the angle or the angular separation, so this distance function, and sometimes one cannot write it, so distance is theta, and then use theta in the next, for the next definitions of quantities, when I had to copy paste again the whole thing, like distance.
Yeah, you can try. Sometimes you have to. Sometimes you can use something like the aliases that I just marked.
But sometimes
that does
it doesn't
not
work.
necessarily work. Yes, indeed. And no, this is well, you have to copy and paste. And that, unfortunately, if that doesn't work, you can try if it's possible to play around with subqueries in that manner, but often you end up with you have to repeat that, and that's the big difference here. These aliases are not variables. They don't behave like variables, unfortunately.
Can I add something here? When we're developing the ADQL language, it is a trade-off. It's a compromise. And the compromise is between language complexity and portability. So earlier on, there was another question in the list about how does the ADQL cope with different database platforms, for instance, MySQL, and I can't remember what the other database platform was, but for instance, MySQL, Postgres, or SQL Server. And so we had to come up with a compromise of a subset of the language that all of the database platforms would be able to cope with. And when you get into, in full-blown SQL, there's a lot of things like subqueries, nested subqueries. Different database platforms handle those differently. So the more complexity we added to ADQL, the fewer database platforms we could support. So it is a compromise between those. Yeah.
And maybe like a workaround would be to combine Python with ADQL, and everywhere where there's like some copy paste thing, then use Python for.
That's the that's the next 45 minutes where we show you what you do with that. But I want to go back to Haru Fakauta said a few things. First of all, of course, you're right. And UCD M-opt means electromagnetic in the optical band. My bad. Thank you. I wish you were loud. So yeah, I was talking rubbish here. It's early in the morning for all of us. But nevertheless, I should get myself a paperback and walk around with that on my face for the rest of the day. You're right, Haru, of course. Then you said that Topcat itself parses the ADQL. Well, of course, it has to know what's the tap, what's the tap upload in there, or the tap uploads in there. So, in this regard, it has to parse that part of the of the query. And as far as I know, Topcat elaborates on if you do mistakes already, if the query does make any sense. So, and not elaborates, it does a little analysis and supports you with that anyway.
Yeah.
So Luis da Costa had a question.
I think that's been answered.
Oh, no, the question, how the ADQL handles different databases at different services, and then, for example, MySQL, and the other one is Postgres.
Yeah.
Yeah, that's one for you, Dave, not for me.
Okay, so that's been answered in the, there should be an answer in the text, but if, in the chat, but if not. So, yeah, the server side, ADQL is a subset of these languages. So the server translates ADQL into the specific dialect for the database that you're looking at. So the astronomer doesn't need to know whether you've got MySQL, Postgres, Oracle, SQL Server. ADQL means that they all look the same, and so you can apply the same query language and the same query to all of them. And yes, the server side then does the translation.
Okay. I think for the sake of time, I will continue with pyVO and ObsTAP. Still, if you have questions, comments, critique, please just throw it in. I will try to better myself. I will try to answer and to support you with whatever I do. So there is the first Q&A already. Well, I can't even see it anyway. Okay, I will continue with the pyVO part here. Therefore, again, I will close Topcat now to have a vanilla version of Topcat here, and it might confuse you. I will open it in the background, though I actually want to will present pyVO here, but we will work with Topcat, or we will see a few things in Topcat soon. So that's why I keep it here. So clear this here and go into the PySources. So the first example that we want to give you, or we've introduced you shortly to pyVO. pyVO is the Python API to the VO standards, and it's a package affiliated to AstroPy. So a lot of or the results that you gain when you query a service, for instance, will be AstroPy tables that you can use or treat like AstroPy tables, and you can use that. So you are in an environment, if you're familiar with AstroPy, you can use that. We have a few examples on how pyVO may work. So we start with the example 1, and this is just a very simple example so that you can see what is going on here. So what we need is we import pyVO. There are two lines that we also import, and these are due to sanity, our sanity, if we work with that. So basically what these two lines do is they suppress warnings. And that is due to pyVO complaints when things are not working properly. And on the base that if you start programming, a lot of things don't work properly. So there might be that there is one reply from a service claims to be following a more recent version of a standard, but in fact it does not yet. It just, by what mistake ever. And this happens a lot. I mean, people are involved. There are humans involved. There are mistakes happen. That's just like that. And warnings are good. They show you that something is not going as expected, but it's not a reason to break the thing. So if we perform queries, often there will be a warning. If you perform these queries in Topcat, you will not see the warning. It's like if you access a web page through a browser and things are slightly off on the web page that are not according to the HTML standards that they claim to be. Well, if browsers would break and not show web pages, you'd be surprised how broke the internet would be. So the same goes here. For the sake of the tutorial, we just suppress the warnings here. If you're interested, of course, well, delete these lines and you see the warnings, and then you get the idea why we do it. We don't have anything to hide. We will have a script later where you don't skip the warnings, where we simply show you this is really what's going on in the background, and then you see why sometimes kicking out the warnings might be of importance. So these two lines are just for the warnings. Then we build a service object here, and we do this in a conventional way, which is the pyVO convention. So we have pyVO, which is the package that we imported here, or the library that we imported here, and we say in pyVO we use the data access layer. So dull is the data access layer. Data access layer is in the VO the part where data access happens. That means data access happens in the cone search, in a TAP service, in a simple image access simple image access protocol. Yes, in the simple spectral access protocol. This is where data access happens, and that is the data access layer. So any of these kinds of services you can start with, well, pyVO, dull, TAP service, or SCS service. Give you in a minute you will see an example for that, how you can use that. And well, then you have parameters for the service. Usually at least the URL, well, you need at least the URL to the service. Some services may demand more information, but some protocols may demand more information for that. In the case of the TAP service that we have here, we can use the service object that we built here to use the method search and perform this simple search here. So, which is, well, a very simple ADQL query where we just say, take the first result from the table ivoa.obscore. And then we take the result and simply write it to a local file, result.vot. So I'm quitting that, and I'm going to perform that query. There is, see, actually nothing happens except for the fact that I now have this table here that performed the query. I can have a look into this table so that you can see what a VO table actually looks like. And I think that would be the right moment for Dave to step in to talk about VO tables. Oh, maybe we lost Dave. Dave? Oh, okay.
Sorry, I was on mute.
Oh, sorry.
Panic for the mute button. Can you pop up a web browser looking at the
oh, yeah. Oh, well.
Explanation page?
Maybe I can. Maybe I can. Hang on.
Yes, the one. Thank you.
Yeah.
Okay. So so this section is for the technical geeks rather than the astronomers. So if you're interested in what it's doing underneath, so this is replicating what Hendrik just did in Python, but I'm using curl to send the requests and then actually printing out what the requests are happening. So this is sending a GET request. And I need three parameters. I need language equals ADQL, and then I need the actual query itself, and I need the endpoint of the URL of the service I'm sending it to. So all three of those are defined in the syntax for those is defined in the TAP specification. So all TAP services behave the same way. And this is just sending a simple HTTP GET request. And in the next block, it shows you actually what's sent on the, so this is actually what's sent on the wire. This is actually what gets sent across the network to the web server at the other end. And you can see the query ends up encoded, replacing spaces with %2 zeros. So URL encoded and escaped all the special characters and sending it to the web server. The service then responds with a VO table response. And so this is the other part of the standard, is you get a standard reply from the server. So the Python or Topcat knows what to expect in the response. One part, so this is showing here two of the fields in the metadata, in the header of the response. And it's showing the human readable description is the description of RA center of observation. But then the line above that has all of the machine readable data. So it's describing the data type and then the UCD, which Hendrik has already covered. And then it's also supplying the units and then the U type. And the U type is a link into the data model that's behind this service. So all of that enables the client application, either your Python program or something like Topcat or Aladin. All of this machine readable metadata enables the client to understand how to handle the response. And then the bottom section below that is, in this particular response, we get the data encoded as a binary stream. So this is encoding the data this way. It's much more efficient in terms of space and much more accurate. And then the pyVO can read that, decode it, and actually produce the values that you actually see. So that's kind of that's a brief glimpse as to what's actually happening. The two lines of the that Hendrik had in his Python. This is the client server interaction that's happening, but it's also the standards that are behind that mean that all of the TAP services behave in the same way. Okay.
Yep. So hang on. I admit Zoom is behaving a bit weird for me, but so it's hard for me to keep track of question and answers. So maybe if there are questions coming up, somebody may check. So as Dave just said, this is what a VO table looks like. It's give you that. It's not really nice to read. Some people are familiar with that, but those are, well, really geeks then. And yeah, but this is actually what's not necessary, but this is what makes it feasible. to know a lot of things about the data that you have. I mean, if we have very easy data in here, like marking with the UCD a position or whatever, that makes the life of the average astronomer much easier. So, okay, now we proceed to our example 2, which now is again a very simple example here, as you see. And here you see this is the same, and basically it's the same or a very similar query than we used for the TAP service, except now we're not using the TAP service to query here. Now we are again using querying a cone search service. And as I said before, if I use the pyVO, if I use pyVO, I can simply build a service object by using the data access layer method of pyVO, and then refer to the service. And here you see, well, we lead the link to the KM3net, which is the very same service that we used before. Here you see the small difference between the for the cone search service, again, or the difference between the cone search and the TAP query. Of course, TAP query was a bit more powerful, a bit more elaborated, but and here, well, I again need to give a position as a tuple with in decimal degrees, and I give a radius also in decimal degrees. And if you remember, last time I gave a radius in 30 degrees. Now I'm giving a radius in 3 degrees because for the following queries, I don't want to have too many objects in here. We will have again, we save the data locally, but here's the reason why I restarted Topcat. We do something where we say the results that we defined here as neutrinos, we use that and broadcast that. Well, we do a method broadcast SAMP to Topcat here. Before we do that, this here, I will show you briefly how we can build a service, this service object here, using IPython. IPython is is a command line version of Python, and it's a very nice one because it comes with TAP extension, so you don't have to type a lot. So I can simply import pyVO as I type. I type the exact same lines as I would use to type in the script. I could copy and paste them here, but for the sake of demonstration, I will simply type it and show you how easy it is. So I start with pyVO here to show, whoops, why. So now I have my pyVO object, and I simply pressed tab here once. And then I see the methods and attributes that I can have with pyVO here. And then you already get ideas like there's something like registry here, there's something like SAM, there is something like input-output that might help us. But what I'm actually interested in is the data access layer, which is here. And under the data access layer now, I find a lot of things related to the data access again. And especially I find something like the simple cone search query, the simple cone search record, or the simple cone search service. And these are all attributes that I can give when I do this. I also have the simple access service here that I can use. And here I have the simple spectral access service here. And I have the TAP service here. And all these services basically follow the same rule. If I know the URL of a service, I can use these methods or these attributes to define these methods to define an according service. And here I want to define the simple comb search service. So sorry, I will simply type the URL into this. /20_01. Here, of course, I cannot use tab extension because, well, that's simply the string here, and yet not the script cannot know anything about this scs.xml. Now I'm curious, is that HTTP looks,
yep, that looks good.
That looks good. So, and this so far, why did I double check it? Well, because if I write something wrong in here, nothing happens. The service protocol itself, the service object itself, does not do anything yet. The service, well, what I need is, I need something like not neutrino symbol. I need to define something in here. So I go for my neutrinos. Now I can use the tab extension to use, well, again, the service object comes with a few methods. One of these methods is the search method. And in the search method, I need to define a position, which is a tuple, sorry, and it's 4335, and I define a radius and of, well, let's say 3 here. Does that look good? That does look good. If it doesn't work, it will complain immediately. Okay, so the search worked, and I can now use the result object of the neutrinos to download or to save the VO table. And here's the important bit. This bit here, that was that makes actually the XML out of the binary. That's why if I look into the VO table, I will see XML data there and not binary data. But of course, you can use it to save the binary data, doesn't matter. And neutrinos.vot. So that's what I want to save. So, and now there is the actual fun part. You see, this is my Topcat that I started a bit earlier, and it's a vanilla Topcat. And there is a nice little VO standard and protocol that is SAMP. And each of my result objects, and that really goes for each result that I receive from the VO. Each of these objects comes with a few very, very useful methods. The one I used to save the XML file, save the XML file, the VO table to my machine is one. And another one is the broadcast SAMP, where I simply can say where to broadcast data. So if you look what happens, if I'm in my pyVO and just sent the stuff, Topcat reacted and took some data. What Topcat took was, well, the XML data, simply the result from our cone search. And now I have this very same data in Topcat. And if you remember, when we performed the query in Topcat in the cone search service, well, we had exactly this data structure. We had exactly this metadata. So just by using the standard of the cone search, just now I took it from pyVO instead of from the Topcat cone search, but the data, how to access the data was exactly the same way. So it's the same data that is transported that I now have in Topcat here. Of course, there was the difference that I used a different or smaller radius when I performed the cone search. But this shows how easy it actually is to work with these pyVO and with the data, and how easy it is to explore all of that. And it follows a very, very good convention, a very easy to understand convention, how to use the data. And you can play around here. You can really say, okay, I'm only interested in some results, please send them to Topcat or whatever. So that's a very, very, very useful tool in pyVO.
Sorry, there is a question from Patrick here, and Patrick is asking whether or not it's possible to get a list of all the URLs that you can access via this SCSS service.
Yes. Yes. In 2 examples. Patrick, if you're a fast guy, go to example 4, read the example 4. You may get an idea, indeed already, you may get an idea which part you may have to change in example 4 to make it for a cone search. It's not, example 4 is doing exactly that, a VO query. And we will come to that after example 3. So, speaking of example 3, that is where we are heading now. Okay, I'm making this big. Example 3 now is a bit bigger. Example 3 is a bit broke. Sorry. Maybe I messed this up with all of you. There might be, yep, yeah, there's a swap that I hope I didn't. I fear I messed it up for all of you. I'm very sorry. I will delete this file from the repository. So only if you're using VI then, or VI derivative, then you may suffer from this problem. Yeah, I'm a dinosaur in that meaning. So again, you already see example 3 is a bit longer, but now we're doing a few things, and we start with familiar things. We import pyVO. In this example, we also import from AstroPy table. We import the table class. We will need it to read data, to read the VO tables from the file system. We also have the warn options here. Again, say, are we ignoring the warning options here? And we have a query, which is a special query. So what is happening here in the script? In this line, we are reading the result from the example 2. So that is the VO table containing the neutrinos events that we took from the cone search service from KM3net just a few minutes ago. And we use this by using table read, because this is the input-output class AstroPy provides to access a VO table. We also say this is VO table. So this is an AstroPy table in the end. This is an AstroPy table object that we use. We do this, the exception, ignore it. That's just if something broke in example 2, then we have a fallback here. We won't need that because that worked well. We make the service object, well, as you know, the service pyVO data access layer tab service and the URL for the Gaio data center. Now, there is something special here, and that is the result now is service run asynchronously. This is not what we did with the tab service in example 1. And the reason is, one, it might take a bit longer what we're querying here. So we are running it asynchronously. And the second reason is that we need to upload stuff. What do we need to upload? Well, the AstroPy table object that contains our neutrino events. So here I define which is my upload file, and this is a dictionary. So here I could add, we had the question, can we upload more than one table at a time in a join upload? Yeah, yes. And here I can define a dictionary where I refer to these uploads. And as you see, I'm referring to the upload here at this point, tab upload lt.lt. I give this upload the alias mine, because it's my data that I'm uploading here. And this now, then indeed, I use mine array, I use mine decal, and I use mine beta. This now is the range. And you see why I chose to, why I went for fewer objects, because here I'm querying in a wider range. There is something odd though here, and that is this line here. Here I say, well, the upper part, you know, I'm selecting, well, the top 50 results. So the first 50, I take everything now, and from a table in the database, I perform the join with my upload, with my local data. So I put a bit of the data to the code. I have the geometry. So I define a circle around each data point from my table, defined by array dec, and the column beta as a radius around them. I define the circle, and I check if in the remote database, if the geometry defined by the position in the remote database, if this point is contained in the circle, which means one contains SQL does not know Boolean. So this is the poor man's Boolean in SQL. So if this function is positive, it will, if it finds a match, it will return the value 1. So I'm checking if that is the value 1, then, well, join the two databases at the two data sets at this point. And well, I added a condition, and the condition is where DB data product type is image. Now, what I'm querying here is a very, very special, the very special table. And this is the so-called ObsCore table. This answers a few of the questions we had, and a few questions that we had before. First of all, whenever you find an ObsCore service out in the world, this ObsCore service has this table. And this table has predefined columns. And these columns have the same names. You can refer to these across all ObsCore services. One or two of these columns are S and array and SDEC, well, which contain obviously the position here. ObsCore stands for observational data. And what I can do with this is basically asking the question to a server, to an ObsCore service, do you have data of that kind that I am searching for instance, image data, at a specific position? And now, well, think a lot more in a given wavelength, maybe at a given time, if I'm interested in events, of course. Do you have this data? And if you have it, what do you reply? So maybe Dave wants to add a bit to the ObsCore of what I just said.
No, I think it's so, yeah, when a service registers itself as ObsCore, what it's saying is it supports this view. So all the archives themselves have, each of the different science archives have different table structures, but then each service that represents itself as an ObsCore service has also got this one common view, so that you can apply this query to all of the services. Yeah.
That's the crucial part. I can take this very query here, this bit here. Oops, I have to scroll a bit up. So this where I define my query. This is the query. I can take this query, and this query I can copy and paste to all services, or as I don't want to do this, this is Python. I mean, come on. I define the query once, and I can have, maybe I can take a list of services, ObsCore services, and then I simply send this query to all of these ObsCore services. I can do this. This is example 4, which we will see in a minute. But before we do that, we will have a look what happens after we query, after we send this query, and what actually happens. Well, we don't see example 4 in a minute. It will take a bit longer for good reasons. So I run this query here. This is the line where this query is run, and you see actually how tidied all this script is. I give you that. If you in the real world, you need a bit more here and then to make things run smoothly. But to get results, you really get very fast with code that is as slim as this one. And I don't even bother with saving this result to the hard drive here. I simply pass all of that to Topcat via SAMP. So I quit this, and well, where's my Topcat main window? Here's my Topcat main window. So I will make this a bit smaller here. So that you see what's going on here. Well, you don't see much going on because I'm suppressing the warnings, but you saw there's the result. And the result has, I have 4 as the result here. And now let's have a look into this data. And you see, well, there is not much data in, but what's in the data. That is the crucial bit. In this data, I see in the very beginning, there is a data product type, and it says image. And then I see, well, something like ops collection. Well, that's explaining something with that. I have an ops ID. I have, well, things like this. But do I have image data here? Well, this is Topcat. I hope it's not an insult to Mark, but Topcat can deal a bit with images, but it's not dedicated to images. So actually, maybe I can send all this, what I have in here, to a software that can work with images. So, well, I will do this. I will simply start Aladin, which is the software developed at the CDS for image access and image analysis. And yep, here, nope, not yet. So Aladin is taking some time. Again, I'm just opening Aladin, and you may have noticed things happen here in Aladin. For instance, this took a while to come in here. But what Aladin does when it starts, well, it's querying the VOs in a standardized way and asks for, these are image services here. There is a lot to say about how this part actually works here. That's very cool, but that's a different tutorial. Just to say, this is really, this is really cool. Yeah, maybe by the end of the tutorial, I will show you something about that, but this is a bit mind-blowing. So cool it is. But what I actually want to do is I have my results table here and I send it to Aladin. And I can do this in via SAMP now, because here you in Topcat, you see this small thing down here. This button here is the so-called SAMP hub. So the SAMP hub is organizing the VO SAMP tools that can connect to SAMP. So connected to SAMP is Topcat and Aladin right now. This button says connect or reconnect to the hub. I don't need that. But what I can do is, oops, I can click on broadcast, and then the whole table will just be broadcast to any SAMP application listening. Listening was Aladin, and you see there is the results table down here. And I will do double click here, and then you see the table opens below here. So first of all, we'll zoom out here to give you an idea what's happening here. So if I zoom out, then you see first of all, you see things happening here, right? So what's happening there is when I zoom in and out, I have positions. You can see in this line up here, you can see how this changes according to where I go. And the green dots here actually show me services that have data in my field of view. And you see how fancy this already is, because this works with these standards. With these are image data, so there is ObsCore involved, saying, well, do you have image data in this point of view right now? And this query is really fast going on to tell people what to do. That's the fancy bit that I was referring to, but there is more that I can use. I have data to images here. I don't have the images here. I have links to images and a lot of metadata here. So if I hover over these data here, then you see this red rectangle in different shapes and in different positions. And this basically shows me the coverage of, well, the images that I have here. I did not download the images yet. All I have is the metadata on these images, and I can just by hovering over them, I can see, oh, okay, it seems they cover this. Now, I can look into these metadata of these images and see what's the collection. Well, this is a collection from Hamburg. This is again, this is the big Schmidt mirror in Hamburg that observed this. I can have yeah, well, I have the position where this all this is going on. I do have observation time from minimum to maximum here. I have the overall exposure time. I could have, maybe I could have resolution or more data here about the spectrum maybe. I do have object UCDs here. So metadata that's telling me something. There is a facility name like Hamburg Bergedorf, which is the observatory, Hamburg Observatory. There is the States Observatory at Heidelberg. And of course, these all is data that we provide, or not we, that is provided by the Gavo Data Center. Apologies that I'm not at ARI anymore, sorry. That's provided by the Gavo Data Center at ARI. So, now I won't take the risk to download these images just because, well, they could be big. But what I can do is there is a preview provided, and because there is an access URL, I can simply click on this button here, and Aladin will start downloading the data. I double clicked, so you see this. Now I give you this data does not say much about I will delete one of these, does not say much about my actual positions that I wanted here, and you don't see much on this on any of these images. But for the sake of the possibilities, this is quite a nice example of what is possible. So I go back here and maybe oh, this is a big one here, so maybe if we take, well, let's take this one and see. Yeah, here you see, well, this is a plate scan, obviously. There are information for that. So certainly these images won't show a neutrino event. So these scans are from the 1950s, late 1950s. Certainly they won't show our neutrino event. And but you see, what I can do if I just search, if I search for these ObsCore tables. What I could also have done is in my script. So in the query here, I could have added a line where I refer to the columns where the start minimum time and the maximum time of the observation data was given, which I could have somehow linked to the neutrinos, because I know the time of the neutrino event was in Julian date. So I could ask for that, but it's not a big surprise that this so far does not give many results. And I tried to start with all VO queries for that did not come far with that. So it's not a big surprise. I mean, we're talking about 8,000 neutrinos in the catalog that we at most from the M3net catalog, the entire data in there. And if somebody had found the supernova in observational data from these neutrinos, yeah, that would have been before this tutorial. There's no big surprise here, actually. But it's something that you can keep in mind, and you see what you actually can do with the data already, though there is no big surprise. Now, there was the question about, can I send queries everywhere, through everywhere, basically? So, and the answer is yes, I can. This is example 4. Again, I import by pyVO, I import AstroPy table. You see, I don't import the warning suppression for good reasons. Here, I want to show you what that means, and it's not, we don't have to hide anything, and the colleagues in the VO don't have to hide anything. It gives you a good example what you have to take care on if you do a real world query. So here I follow the Python good Python standards of defining a main function that actually does where I actually refer to my functions then up. So there is my again, I access the neutrinos data from the example 2. That's what I already have. I use this function. I define. Hang on.
Yep, that's so you.
Yeah, here.
Yeah.
Oh, yeah. Here is the actual. So here I define an ops service. So I define a query here. I define the service. Sorry, I'm lost. I define the service object, pyVO, and now I define the registry search. And here, and I say the registry search shall be, well, I'm searching for the data model obscure. So there is no secret here. What I'm doing is I'm basically simply I basically simply want to have a list of all obscure services in that the registry knows about. And if I have this, I will save it to the locally, but I will also pass it to the function ops services here, and this function is this one here. So it takes the list of services and it takes the local data. It will give me a short hint which service it's going to query. Then it will make the service object for Python _tap service. We know that already. Here you see I'm iterating over all the rows in services, and from the row I will take the access URL. So this is the method that just returns me with the URL to the service that I had before. Here's my list of all services that I can use, and I define that the result object shall be, if you run all of that asynchronously with the query and my uploads, we know that. Again, this is the query that we have here. And the results, as they come in, just broadcast everything to Topcat. Here is a bit of stuff. I need the keyboard interrupt here. If things get slow, I want to be able simply to interrupt the query, and there might be exceptions because some queries will simply be broke, but I won't suppress these. I will show these and give a reason what might be broke. So you see, well, we don't hide things. This now is really searching the whole VO for the data. So the first step is, there always has to be 2 steps. The first step is query the registry to find services of interest for you. And the second step is query the service that you're interested in, or query the services that you are interested in. In the case of ObsCore, I can use the very same query for one ObsCore service I can use for every ObsCore service of my interest. And this is what we're doing with example 4. We will run.
Sorry, we have less than 5 minutes to go.
Yeah, lucky me. we will see, hopefully see a bit coming in. So we run example 4, and then you see about this was the table. Here come the warnings, the first warnings, and you see the AIP service wasn't happy with our query. By the way, I don't know why. AstroWeb is coming, and we get some messages there. Haro, don't be afraid. This just means that the result is empty. So there is no VO table coming, or no real answer coming from your service. Doesn't mean your service is broke. That's the typical query. This one takes the time, and just have a look in Topcat if. There it is, the Topcat window. No, there's not yet. So in Topcat, whenever one of these services might get a result, we may see it in Topcat. And now I'm getting impatient because this service takes a long time. I will just interrupt that. And it goes to the next one. Yeah, here you even have a service error. We cannot pass the daytime here. So you see, unfortunately, there is a lot some errors are coming in, and in between you see errors like this one, which basically means the query was okay, but the result that came back is empty. So the Armenian VO will also take a while. I'm getting impatient with this. CADC might give us a result. And you see, this is the, well, let's let the all VO query run in the background, and I will simply take, I think we are simply taking questions now. If we see any results, we will see that. So are there any questions? There is at least one.
So folks, well, fantastic tutorial, by the way. Just so that you know, we had something like 70 people watching between Zoom and YouTube. It might actually be a record for ADAS. So congratulations, folks. You've done a great job. If there are any questions, we might have time for maybe 1-2 questions. Otherwise, there is a tutorials channel newly created. Great suggestion, by the way. In Discord, you can keep the conversation going there as well. So any question? Oh, there is one person with the hands up. So you can now ask your question. Is Haro?
Pretty awesome tutorial indeed. Thank you.
Thank you, Harold. Hi.
Hi. I'm a bit surprised by you doing this example 4, that so many errors happen, because it's all standard IVOA ObsCore queries. So why is it even working? I mean, I haven't seen any positive results so far.
Oh, you haven't seen any positive results because we have, if you see, we have just four rows in there, and there is not much data maybe related to that. So
no, okay, no, but that's is that due to no data being present, or is it caused by the errors?
It might be both. It might be both. You see, if this error here, the ISO archive is just, well, that's a 404. They don't even have these. So this, this is not reachable here, yeah, then you see, if you go into the arrows, then you see a lot of these arrows that are kind of broke. They're just coming in, these 404s, and indeed this is something to complain about. And one result of this tutorial will be that we contact these services and say, well, you claim to be an OBSCORE service, but you're not really compliant, and things happen that are not as or they're going not as smoothly as expected.
No, I mean, if you're trying to do something real, if you're trying to do real science with this, it's really sort of going completely against the point of the VO, if I'm being a bit skeptical.
You are right. It's well, if you see it as, yeah, as you cannot use it right now because there are few results coming in, or there are errors coming in. Yes, you are right. What if it doesn't work perfectly, yeah, maybe if I take a few more objects, maybe if I actually, yes, there is one result as we have right now, which I expected to come in because these are the time series. You see in Topcat, these are the time series that we have that come up from the Gaia service, from the OBSCORE service. So there are two reasons for that. The first reason is we have more than 100 TAP services out there, but I think roughly 35 OBSCORE services. And many of these OBSCORE services are not well maintained these days, and this needs to be fixed. This is right. Nevertheless, if I want to advertise OBSCORE and say this is how OBSCORE works, I can only work with what is there. I can only show what is working and how it's working. And there is very few data out there right now related to OBSCORE. Hopefully more data will come in. Hint, I know you are working on that. And and we want to prepare people for this. I give you that. It would be nicer for marketing reasons to show people, oh, it's working perfectly, but that's not how the world how it's going to work. This how it is actually. There will always be things going wrong, and they go not smoothly, and then you need to show people, yeah, this is how you can do this, how you can work around this. So if I give you the example 4, it's very, very, very simple things in Python in example 4. You may not believe that, but this exception here actually simply this try and the exception here together just is the reason why the script doesn't break. And because with the first, if I don't do this with the first service, not giving the right answer, everything will break, and that's simply not what I want what should happen, right? So so I want to show the real world and how you can prepare for that and how you can use it if things are out there, or if the services are better maintained in future. And yes, from the VO side, this is a good reason to say, well, maintain your services in a more appropriate way. Do it better. And to be very frank, there are services well maintained out there that run smoothly and that are reliable, and the data in there is in OBSCORE. And I don't see why I shouldn't present data on these services, or should present how I can present these services, because other services are broke. And I don't want to blame anybody, because there is no reason. I mean, if you look at the services of many of the services that were formerly known as Astrogrid, they simply broke because funding ran out. So the maintenance there is not guaranteed. And but that is not an issue that I can say, or that I can leave with people and say, yeah, well, that's an issue, that's a structural issue of how do we do this funding for this, for this stuff. And that doesn't leave me to say these standards are there to work in this way. And if you want to search for data in this, for observational data, this is the way how you can do it. There is not much right now. Force people to publish their data in this way. I know you are working on that, to do that, to publish it in that way. And I know LSST will do it in this way. So Gaia is doing it, certainly doing it in this way. So and the ESA archive is doing that in that way. So there are people, and I forgot a lot of people here. Yes, of course, the CDS, Vizier, I forgot a lot of people, my former employer, and ESO, they are all working on this. And some services, well, break. But those services who put a lot of effort into this, those people, well, I'm happy to present their data and to show this is the way how you can do it. And this is the way how you can do it in a standardized way. If people feeling discouraged now to use the VO, I'm very unhappy about that, but it's better to present something and show there is something going on. And I think it's better to show, yes, some wires are sticking out than to pretend they wouldn't. And to show people how you can do that. And still, yeah, you have to think about some wires are sticking out. And a big advice, if you find some wire sticking out, something is not working, contact the people, submit a bug report, tell people, oh, it's not working as expected. The worst that can happen is these people fix the service. And
no, it was not meant as criticism. It was more,
yeah, I know.
It was surprise, actually.
So, yeah, well, I don't see why I shouldn't present the good stuff and at the same moment say things don't work very well. I don't want to sell you a Volkswagen, you know. That's
well, thank you so much, folks. We are running out of time. It's a great discussion. You can continue on Discord. There is a tutorials channel also on Discord. You can create multi-people chat rooms, and you can continue this discussion. I know Alberto has something to say. Mark also, Christophe as well. Excellent tutorial. Really amazing tutorial, and I'm sure lots of people will also watch it on YouTube later on this afternoon and in the coming days. Thank you so much to both of you for your time, and I learned a ton of stuff, and I'm very, very grateful for you folks taking the time to prepare the tutorial. We know it's a lot of work, and we definitely appreciate it. Thank you so much.
Thank you for giving us the opportunity. And I hope we were good openers for the ADAs.
Oh, absolutely. It was a fantastic tutorial, 70 people, unbelievable, totally unbelievable. For everybody else, you can continue the discussion on Discord. And of course, there is a new session coming up in a few hours so that we have time to have some breakfast and or dinner, depending where you are, and all of that. So I will see you again in a little while. Thank you so much.
Thank you.